So today we're going to look at how we can determine the standard electrode potentials, okay, for half cells or electrodes where we have non-metals in equilibrium with their ions, okay. So for example, let's say that I wanted to determine the standard reduction potential for the chlorine fluoride half cell, okay, or this particular electrode. So over here again, there's no metal involved in the equilibrium, so we're going to use a platinum electrode, right? So we want to determine the standard reduction potential for the following equilibrium, right? We have Cl2 plus 2 electrons forming 2Cl minus, right? And we want to find the standard reduction potential for this particular half cell. So here we have chlorine gas at 298 Kelvin, 1 atmospheric pressure. And again, we want to determine the standard electrode potential. So this will be connected to the standard hydrogen electrode, right? We have our voltmeter to measure the potential difference, right? And then this guy, here we have a platinum electrode, right? And again, we have a gas delivery system. Right? And here we have hydrogen gas coming in at again 298 Kelvin and 1 atmospheric pressure. Okay. Hydrogen gas at 298 Kelvin and 1 atmospheric pressure, right? For any standard potential, whether standard electrode potential or standard cell potential, we'll always be using a temperature. It'll always be at a temperature of 298 Kelvin, 1 atmospheric pressure, using 1 mole per dm cube solutions, right? So we have 1 mole per dm cube H plus, and then to complete the circuit, right, we have a salt bridge. So this is our salt bridge. Of course, in the standard hydrogen electrode, we also have a platinum electrode, okay? And again, if you are asked to draw a label diagram, also label the voltmeter. Now you want to determine the standard reduction potential for this chlorine chloride half cell, right? We want to determine the standard reduction potential for this guy. And we know that the standard reduction potential for the hydrogen electrode is defined to be 0.00 volts, right? E naught is 0.00 volts, right? Now it's observed, okay, that in this particular reaction, so in this particular case, okay, we are able to determine that electrons flow from the standard hydrogen electrode. They flow from the standard hydrogen electrode towards the chlorine chloride electrode, okay, towards this half cell. So we have a flow of electrons from the standard hydrogen electrode to the chlorine chloride half cell, right? Which tells us that our oxidizing agent here is chlorine, right? Chlorine is accepting electrons, it's undergoing reduction, that's going to be our oxidizing agent, and hydrogen is losing electrons, okay, it's going to be our is going to be our reducing agent, right? It's undergoing oxidation. So here we can say that chlorine is gaining electrons to form chloride ions, okay, and then hydrogen is losing electrons to form H plus and electrons, okay. So we can say that if we compare the relative strengths, right, if you look at the oxidizing agents present here, those are the species undergoing reduction. We can say that chlorine is a better oxidizing agent than H plus, okay. Chlorine is a better oxidizing agent than H plus, and as far as reducing agents are concerned, hydrogen gas is a better reducing agent than chloride ions. Since we know that of the two, again, chlorine accepts electrons, it undergoes reduction, it's the better oxidizing agent, and hydrogen loses electrons instead of chloride, so hydrogen is the better reducing agent, undergoes oxidation more readily. So over here it's observed that the EMF of the cell is found to be 1.36 volts. Okay, positive 1.36 volts. So what is the standard reduction potential for this half cell? Standard hydrogen electrode is obviously assigned a value of 0 here, right? So this one will either be positive 1.36 or negative 1.36. Now we know that chlorine undergoes reduction more readily than H plus. In other words, it's a better oxidizing agent, and therefore the standard reduction potential will be positive 1.36. Okay. So we're able to determine the standard reduction potential. Right, by connecting this half cell to the standard hydrogen electrode. Another way to think about this, right, here we have this, the standard hydrogen electrode is our negative terminal, right, and the chlorine chloride half cell is our positive terminal, right? This is our positive terminal. So we know that when compared to the standard hydrogen electrode, since this is the positive terminal, it will have a positive standard reduction potential, right? And that potential value is determined by looking at the voltmeter. Okay, but again, conceptually, since it's a better oxidizing agent, remember the standard reduction potential is a measure of strength as oxidizing agents. It's a better oxidizing agent, right? Its standard reduction potential will be positive. It's a better oxidizing agent than H plus. Here, obviously, our cathode is the chlorine electrode, right? Our cathode is this platinum electrode, right? Then the chlorine chloride half cell, and then that's where we have reduction taking place, right? Accepting electrons, gain of electrons, and then anode is where oxidation takes place, right? That's our hydrogen electrode, right? Standard hydrogen electrode. And then if you look at the overall equation for this reaction, right? The overall equation that we have for this reaction, we have Cl2 plus H2 forms 2H plus and 2Cl minus. So obviously here, if you look at the half equations, right, this half equation has a potential of 1.36, right, positive 1.36, and then obviously the hydrogen one has a potential of 0.00 volts, right, and then the sum of the two gives us the overall EMF of the cell.